Motion changes sound. A city street pulses with life. In the distance, an ambulance rushes forward, lights flashing, siren echoing sharply through the air. Each note seems to stretch and squeeze as it draws near. To a bystander at the curb, the wailing pitch climbs urgent and high then, as the ambulance speeds past, the sound falls away, dropping into a lower, stretched-out tone. This familiar shift is known as the Doppler Effect, a change in wave frequency caused by motion between the source and observer. Ahead of the moving ambulance, sound waves compress, packed closer together, each crest just behind the last. Behind, the waves stretch out, growing farther apart. The result for someone standing in front: the frequency increases and the pitch rises. Behind, the frequency drops and the sound deepens. This principle is not limited to sound, it affects all waves. In the world of light, the Doppler effect reveals itself as redshift and blueshift. When a star or distant galaxy moves away, its light stretches, drifting toward a deeper red. As it approaches, the light compresses, tinting bluer. Astronomers rely on these color shifts to chart the speed and journey of objects across the cosmos, unlocking secrets of distant worlds and the universe's expansion. This effect shapes technology too. Meteorologists map dangerous storms with Doppler radar, measuring wind and rain in real time. Police use radar to enforce speed limits on busy highways. Even doctors harness Doppler waves to sense the rhythm of blood flowing inside the body, offering a window into heart and health. Motion reshapes waves, altering sound, shifting color, and opening new ways to explore the world around us.